Okay, back to the drawing we were just looking at. That SD card was running out of available space. All right, so here we have separated the hanging wall from the foot wall, and we have our stick figure rock climbing person. They're able to hang from the hanging wall up there on the corner there of the hanging wall. And then notice our stick figure rock climbing person has their feet on the foot wall. This is just a way we try to illustrate the difference between hanging wall and foot wall. Okay, we're now going to move over here and we're going to show the fault trace in a different way. You'll notice this says bird's eye view. So that line coming down the middle, going kind of up and down, that is our fault trace. So imagine that that is, for example, the San Andreas Fault, a strike slip fault, and that's where it intersects the ground surface. If we're flying overhead in an airplane, we can actually see that. We could see the offset there of our creek. Anyway, that's what a fault trace looks like from a bird's eye view. We're now going to take a look at a drawing I have attempted to make here in 3D. Bear with me, I'm not great at drawing 3D, but we see here we have the hanging wall on the right and the foot wall on the left, and we have had movement. The hanging wall has dropped down relative to the foot wall, and in our drawing you see there that place where the ground is kind of exposed. That is our fault scarp, and then that line along the ground surface where the fault plane intersects the ground surface, that is the fault trace. Okay, we're now gonna put all this together and walk over here and learn the different fault types, and if possible I'll demonstrate with the block diagrams, but I did not bring my tripod and I don't have a helper, so that might be difficult. Okay, so notice up there in the top left corner it says number 1, dip slip faults. We're going to have dip slip faults and strike slip faults. We're going to have 3 types of dip slip faults. So this one here, number 1A, is called a normal fault. You'll notice the arrows beneath the word normal are moving away from each other. That is to denote extension or pulling apart, stretching. So we see here hanging wall on the left, foot wall on the right. We see here that the hanging wall has dropped down relative to the foot wall. The angle of the fault plane does not matter on a normal fault. As long as that hanging wall drops down, it's a normal fault. How does this happen? It happens due to extension or pulling apart, stretching apart. That's how you get hanging wall to drop down. Where do we find these kind of faults? And the answer is divergent boundaries, which are going to be our mid-ocean ridges and our rift zones, continental rift zones. Okay, now how about over to our second type of dip slip fault. Okay, this is called, so this is 1B, thrust fault. Notice the arrows beneath the words thrust fault are pointing towards each other. That is trying to show compression, squeezing, coming together. Here we see the hanging walls on the left and the foot wall is on the right. The hanging wall this time has been pushed up over top of the foot wall. So we could say hanging wall moves up relative to foot wall. Why does this happen? Compression, squeezing. And that's why the arrows are moving towards each other. If you squeeze these rocks together at this type of fault, you get the hanging wall to move up. So where do we find compression and squeezing on this planet? And the answer is convergent boundaries. Ocean to continent subduction zones, ocean to ocean subduction zones, and continent to continent collision zones. There is a typo on the board. I meant to have ocean to ocean in there instead of ocean and continent twice, but we're saying it verbally, so it's okay. And the angle of the fault plane here matters, so let's move this back up a little bit. You see there that in dashed lines I have superimposed an XY axis. Y is the 90 degrees, X is the 0 degrees, and then I have a line in the middle that's 45, and you see there that the angle is less than 45 degrees. Okay, so the angle is less than 45 degrees for a thrust fault. Now, one more type of dip slip fault to talk about, and we're going to call this thing the reverse fault. So this is 1C, reverse fault. You see the arrows there, again moving towards each other. This denotes compression or squeezing. Okay, so here we have hanging wall on the right, we have foot wall on the left, and the hanging wall has moved up relative to the foot wall. One thing you might notice right away is that the angle of this fault plane is quite steep indeed. So what else can we say about a reverse fault? Hanging wall moves up relative to foot wall, just like in a thrust fault. This is a result of compression, squeezing, just like in a thrust fault. Where are we going to find this? Convergent boundaries, So again, your ocean to continent and ocean to ocean subduction zones and your continent to continent collision boundaries. Now, what's different about the reverse fault? How is it different from a thrust fault? And the answer is the angle. Yet again, we have an XY axis superimposed on the fault plane. The Y is the 90-degree axis and the X is the 0. And then in the middle there, we have a 45-degree line as a dashed line. And you will notice here that that fault plane is greater than 45 degrees. So it is a steep angle fault. That is the only difference between a thrust fault and a reverse fault, is the angle. All right, let's see if we can get this in here. So our second major type of fault is called a strike-slip fault. So this is number 2, strike-slip fault. All right, so this is, again, a cross-section view. All of these last 4 diagrams here are cross-section views. So you see there where the ground surface is, and this fault plane is vertical, 90 degrees straight up and down. This is going to accommodate lateral movement, lateral motion. And where do we find lateral motion? At transform boundaries. Our best example ever of a transform boundary strike-slip fault is, of course, the San Andreas Fault. At this point, I'm going to stop filming and try to set up the blocks to see if I can film the blocks in action.